Coming to advantages, CORDIC is generally faster than other approaches. When a hardware multiplier is not available, for example microcontrollers, or especially when the number of gates required to implement the functions, its support should be minimized like FPGA or ASICs. These CORDIC multiplier will be used. There are many more suitable for pipelining VLSI array processors. The utility of the CORDIC based architecture lies in the generability and flexibility. It can be used for various biomedical applications, especially in FPGA implementations. It can also even use in neural networks. One of the better applications of a CORDIC algorithm is a polar to rectangular transformation. A logical extension to sine and cosine computer is a polar to Cartesian coordinate transformer. The transformation from polar to Cartesian space is defined by the multiplication by the magnitude comes with the CORDIC rotator. The transform has a gain equal to the rotator gain, which needs to be accounted. If the gain is unacceptable, the polar magnitude may be multiplied by the reciprocal of the rotator gain before it is assigned to the CORDIC rotator. One of the beautiful application will be a general vector rotation. In this, the rotational mode of the CORDIC rotator is also used for performing general vector rotations, as are often encountered in motion correction or any control systems. The rotator rotates the vector to the desired angle. The output will be scaled by the CORDIC rotator gain that must be accounted for the system. If the scaling is unacceptable, a pair of constant multiplier would be required for compensate gain. One more application would be the arc tangent. The vectoring model of this algorithm produces a magnitude of the input vector as a byproduct for the computing the arc tangent. After the vectoring mode, rotation of the vector is aligned with any of the axes. The magnitude of the vector would therefore be the same as the components of a rotator vector. The CORDIC implementation represents a significant hardware saving over an equivalent Pythagoras processors also. One more would be a inverse CORDIC functions. In most cases, if a function is generated by a CORDIC style computer, its inverse can be computed. Unless the CORDIC rotator described is usable to compute several trigonometric functions directly or indirectly. The initial values and modes permit direct computation of sine wave, cosine wave, arc tangent, vector magnitudes and transformations between polar and Cartesian coordinates. One more application would be extension of linear functions. A simple modification of the CORDIC equation permits to the computation of a linear functions also. It performs operations similar to shift and implementation of a multiplier for optimal solutions. The vectoring modes will be more interesting as it provides a method of evaluation ratios. Adding one more application would be extension of hyperbolic term functions. The close relationship between the trigonometric and hyperbolic function suggests the similar architecture that can be computed by these hyperbolic functions. The elemental rotations in the hyperbolic coordinate system do not coverage. However, it cannot be done if certain iterations are repeated. Hyperbolic equivalents for the circular coordinate system can also be computed in a similar manner. The ideal architecture depends on the speed versus area trade-off in an intended application. Here are my few references. Thank you.